Greetings and welcome to Chapter 4, Discrete Random Variables, Lesson 4.2, Mean or Expected Value and Standard Deviation. Get to know the new terminology for this lesson. Click on each of the words, learn its definition and meaning. When you are ready, click Continue. Expected value works hand in hand with the law of large numbers. What that means is when we say something is expected value, it means over the long run, not in the short term. So let's take the coin toss. We have said that heads should come up 50% of the time and tails come up 50% of the times. I ran an experiment where I tossed a coin 500 tosses, and each time I recorded, did I get a head or a tail? If I had a tail, I counted it as 0. If I got a head, that was successful, so I got a 1. The first toss, I got a tail, a 0. Second toss, I got a head, so that's 1. So I went from a 0 to a 1, and now I'm going to start taking the averages of those things. And as I create my tosses, you'll see after 15 tosses, my average of success of heads was only 0.3333. After 117 tosses, my success was 0.5128, so a little bit above 50% of the time I got heads. After 243 tosses, my average of getting ahead was 0.4979, so very, very close to 50%, but not quite there. After 459 tosses, my average was 0.511, and after 500, it was 0.4950. So you see, it kind of hovers around that 50%. So in reality, the more trials that I do, the closer to the expected value of 0.5 it will be. That's what my expected value is. The reality of it is not quite 0.5 until I probably get to about 1,000 tosses. Then it will kind of stabilize to 0.50. Continuing this idea of expected value, let's run through a problem. A men's soccer team plays soccer 0, 1, or 2 days a week. The probability that they play 0 days a week is 0.2. The probability that they will play 1 day a week is 0.5. And the probability that they will play 2 days a week is 0.3. In other words, 20% of the time they play 0 days a week. 50% of the time they play 1 day a week, and 30% of the time they play 2 days a week. We're going to assume that X is the number of days that they play per week. So X will take on the values of 0, 1, and 2. We want to find the long-term average, otherwise known as expected value, or mu, for the days of the week that the men's soccer team plays. Let's fill in our table. Our X values are 0, 1, 2. Our P of X values, our probabilities are 0.2, 0.5, and 0.3. Now to find our expected value, we're going to multiply X by P of X for each of our X values, and then we're going to add up our X times P of X column. That will be our average or our expected value. So 0 times 0.2 is 0. 1 times 0.5 is 0.5. 2 times 0.3 is 0.6. 0 plus 0.5 plus 0.6 is 1.1. Our average is 1.1, meaning they will play 1.1 days per week over a long period of time. The expected value is 1.1, and we would say that the men's soccer team would on average expect to play soccer 1.1 days per week. Let's walk through a little larger problem. Our expected value is the expected number of times per week a newborn baby's crying wakes its mother after midnight. So this data is going to be based on the number of times the baby wakes the mother after midnight and the probability of that happening. We also want to calculate not only the expected value, but the standard deviation as well. So for this particular problem, we know that our x value takes on 0, 1, 2, 3, 4, 5. And the probability that goes along with those is 2 out of 50 moms experienced no wake-ups, 11 out of 50 moms experienced 1, 23 out of 50 experienced 2, 9 out of 50 experienced 3 times the baby woke up, 4 out of 50 experienced 4 times that the baby woke up, and 1 out of 50 experienced 5 times their baby woke up. We multiply both of those together to get our expected value. So 0 times 2 fiftieths is 0. 1 times 11 fiftieths is 11 fiftieths. 2 times 23 fiftieths is 46 fiftieths. 3 times 9 fiftieths is 27 fiftieths. 4 times 4 fiftieths is 16 fiftieths. 5 times 1 50th is 5 50ths. We need to add up this column to get our expected value. So our mu, our expected value, is 0 plus 11 50ths plus 46 50ths plus 27 50ths plus 16 50ths plus 5 50ths. In other words, 105 over 50, or 2.1. The expected number of times per week a newborn baby's crying will wake its mother after midnight is 2.1 times. To calculate the standard deviation, we are going to take our x value, subtract this average of 2.1, square it, and multiply it by the probability. We're going to do this for each of the x values. So 0 minus 2.1 all squared times 0.04 is 0.1764. You do this for each of the values. And you add all those values up. You get 1.05, and you take the square root of it, 1.0247. So the standard deviation of the probability distribution function is 1.0247. Now I want you to take a moment to mull over the work that we did for this problem to not only find the expected value, but to also find the standard deviation. To find the expected value, you kind of have to do this work. It's not bad. It is tedious. Take your x values and multiply it by your p of x corresponding value and add those values up. The standard deviation, you can actually use your TI-84 plus. L1, let it be your x values. L2, let it be your probability values. And yes, you can put your probability values in as 2 divided by 50, 11 divided by 50. Let that be your L2, and then run your normal stats on it to find your standard deviation. So yes, there was a lot of work to find the standard deviation, but use your calculator for that part. For the first part, to find your expected value, just run through a little table. Multiply your x and your p, and then add that column up, and that will be your expected value. Standard deviation, use your calculator. Another way of using expected value is payouts for games of chance. Suppose you play a game which you pick 5 numbers are chosen from 0 to 9. Computer randomly selects these 5 numbers, and all values for each round of picking are available because they replace it. So on the first chance, you get 0 to 9. On the second, 0 to 9. You have to pay $2 to play, but you could profit $100,000 if you match all 5 numbers. Sounds like lotto to me. you will get your $2 back plus the $100,000. If you match all 5 numbers in order, each number has a 1 in 10 chance of being correct. So the first round, you get a 1 in 10 chance of winning because that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 numbers. Only one of those numbers can win. So 1 in 10 chance to be correct. In fact, the second number, you have a 1 in 10 chance to be correct. And the third number, and the fourth number, and the fifth number all have the same chance to be correct, a 1 in 10 chance. If we multiply each of those chances to be correct, 0.1 times 0.1 times 0.1 times 0.1 times 0.1, you will have 0.00001 probability of winning. So your probability of winning is 0.00001. Your probability of losing is 1 minus your probability of winning. In other words, 0.9999 is your probability of losing. Now that we know our x values, we know our p of x values, we can figure out our expected payout for this game of chance. Our x values are negative $2 because we paid, we took it out of our pocket. If we win, we get to put into our pocket $100,000. Our probability of losing is 0.99999. Our probability of winning is 0.00001. If we multiply the x and the p of x, for our x p of x for our lose, we get negative 1.999998. I think I said too many nines, sorry about that. And our win, we get 100,000 times 0.00001. And that gives us 1. Add the last column. If we add those up, we get a negative 0.99998, which is about a negative 1. We would expect, on average, every time we play this game, we will lose $1 for each game. Okay, that's in the long run. Even if we eventually won, we would actually lose about $1 for each game that we played. Could it happen that on the first time you actually play, you win? Yes, but in the long term, mathematically, you would lose. Let's look at another payout for games of chance. This time, we play a game based on a coin. Each game, we toss a coin once. We're going to say the probability of heads is 2/3 and the probability of tails is 1/3. If you toss a head, you pay $6. If you toss a tail, you win $10. If you play this game many times, will you come out ahead? Will you make more money than what you pay out? So the probability of a win is a probability of tails, and therefore 1/3. Probability of a loss is the probability of a heads, which is 2/3. Since we pay out $6 for heads, that's a negative $6. And because tails goes along with a win, that's a positive $10. So lose, we pay to play the negative $6 for our X value. Win, profit for playing $10. Our probability of losing is 2/3. Our probability of winning is 1/3. Multiply straight across to get our expected winnings. So negative 6 times 2/3 is negative 4. 10 times 1/3 is 3.33. Add up this last column, and therefore negative 4 plus 3.33 is minus 0.67. What does that mean, though? On average, we expect to lose approximately 67 cents for every game we play. But remember, when you really play, in reality, you lose $6 or you profit 10. It's just that 67 cents is an expected loss per game. overplaying the game over and over and over, because eventually you will win some and you will lose some. It's just overall, we expect it to be an average loss. So no, you will not come out ahead. You've reached the end of this lesson.